Hi, in this video, column chromatography is discussed. Column chromatography is adaptable to all the major types of chromatography. Adsorption, partition, ion exchange, exclusion, and affinity chromatography are carried out in a column. Columns are usually made up of glass or polyacrylate plastic. Laboratory columns have a diameter of 2 to 70 millimeter and a length of 15 to 150 centimeter. Lengths less than 15 centimeter are also available. The ratio of the column diameter to its length also varies. Mostly choose 1:10 and 1:100. Temperature fluctuations may be harmful for certain chromatographic separations. In that case, columns with a thermostat jacket are used. This figure shows column chromatography with fraction collector. Now let us have a look into the parts of column chromatography. This is the reservoir. This is used to store the mobile phase, and this is the column arrangement, and this one is used to collect the separated compounds. Column packing. The column is fitted in the upright position and its bottom is sealed with the glass foil. The column is now filled to about 1/3 its height with the mobile phase. A thick suspension called slurry of the degassed stationary phase is gently poured into the column with its outlet closed. The upper part of the column is all the while stirred to ensure even packing and to avoid air bubbles. The slurry is usually added till 3/4 of the column is full. The outlet is now opened and the column is stabilized by washing it with mobile phase. A filter paper disc or nylon gauze is then placed on the surface of the column to prevent disturbance during mobile phase or sample addition. Many commercial columns provide an opening at the top which can be fitted with capillary tubing through which solvent drips into the column. This provision decreases the disturbances of the column considerably. To prevent the column from drying, a layer of solvent is always maintained above the column surface. Sample introduction. It is necessary that the sample to be applied reaches the surface of the column below the top layer of the solvent. This can be achieved by sucking the top layer of the solvent out and then carefully pipetting the sample onto the column surface. The sample is allowed to just run into the column. Solvent is then added to the column to a height of 5 to 10 centimeter. The column is then connected to a suitable reservoir which contains more solvent, so that the height of the solvent in the column can be maintained to a height of 5 to 10 centimeter. Column development. Continuous passage of a suitable eluent, that is mobile phase, through the packed column separates the components of the sample applied to the column. This process is known as column development. There are two main techniques of elution. First one is isocratic elution and second one is gradient elution. When a single solvent is used as an eluent during development, the process is known as isocratic separation. However, elution with single solvent is many times not sufficient and satisfactory resolution may not be obtained. In such cases, the pH, ionic strength, or polarity of the eluent is changed with respect to time. This process where the composition of the mobile phase is changed, giving rise to a gradient, is known as gradient illusion. To produce a suitable gradient, two solvents of differing compositions have to be mixed in correct proportions before entering the column. This may be achieved by using a commercially available gradient maker. The gradients used could be continuous or stepwise. Flow rate. Flow rate is expressed as the volume of mobile phase per unit time. This is a very important criterion for suitable column development. For a satisfactory resolution, it is absolutely necessary that the eluent flow should be maintained at a stable rate. The easiest way to maintain a stable flow rate is to use a peristaltic pump to force the eluent onto or out of the column. An increase in the flow rate of the mobile phase through the column leads to shortening of the time necessary for separation. The flow rates used differ with respect to the nature of the sample and the nature of the stationary phase. However, commonly used flow rates fall between 1 to 2 milliliter per minute. Column packing also influences flow rate. Unevenly packed column leads to distortion of the flow, leading to unsatisfactory resolution. More densely packed columns retard the flow of the mobile phase and decrease the flow rate. It is therefore very important to pack the column optimally to obtain a good flow rate. Analysis and collection of effluent. The effluent as it emerges from the column outlet is analyzed. The properties of a particular compound, that is ultraviolet absorption, color or fluorescence, are exploited in its analysis. There are two approaches to analysis of solutes in the effluent. The classical approach, which may be taken recourse to in the absence of a continuous monitoring equipment, is to collect the effluent in equal fractions and to subsequently analyze each fraction for the presence and content of the solute. This approach is not suitable if the number of fractions is too high. The modern approach, therefore, is to continuously monitor the effluent coming out of the column. The monitoring equipment is programmed to read the inherent property of the desired compound, such as the ultraviolet absorption or radioactivity. For example, if the desired sample component is a protein, the monitoring equipment may be a UV monitor and may be programmed to read absorption at 280 nanometer. A wide variety of monitoring equipments, each exploiting a different parameter, are available. For example, fluorescence detectors, polarimeters, voltammeters, refractometric detectors, and conductivity detectors, etc. The electrical signal generated by the detector due to the property of the compound which it is reading is displayed on a chart recorder. Thus, as the compound of interest emerges from the column in the effluent and passes through the flow cell, it is depicted on a chart paper. The area under the peak is proportional to the amount of the compound present. This area may be determined by measuring the height of the peak and its width at half the height. This figure shows an example of the illusion pattern that may be obtained and the way the area of the peak may be calculated. The peaks in this pattern represent individual zones of sample components separated from each other during column development. it is possible to identify each component in the pattern on the basis of its elution volume, the volume of effluent collected which corresponds to the apex of the peak. To quantitate each component, its peak height at the apex A is multiplied with peak width at half height B. Collecting effluent fractions manually can be both boring and time consuming. A range of automatic fraction collectors are available commercially. Column efficiency. Let us assume that a given column can be divided into a number of identical segments such that one equilibrium distribution takes place on each of these segments. Each of these segments is called a theoretical plate. Thus, the number of equilibrations taking place in a column is equal to the number of plates that the column possesses. If two solute components have very small difference in their partition coefficients, they will need a large number of equilibrations before they can be completely resolved from each other. Thus, the column which has a larger number of plates will be better suited for resolving these components, whereas a column which has small number of plates will not be as efficient. Therefore, column efficiency is directly related to the number of plates it possesses. The elution profiles in this figure shows the relation between column length and number of plates. In this figure, elution profile A shows column with small number of plates resolves two substances incompletely, and elution profile B shows increasing the number of plates by increasing the column length increases the resolution, but the peaks are not sharp. And in elution profile C, increasing the number of plates without increasing the column length gives a good resolution with sharp peaks. Columns used in obtaining elution profiles A and B have same column packing, and the column used in obtaining elution profile C has different packing from A and B. Therefore, from elution profile A and B, it is clear that the number of plates directly proportional to column length. Thank you for watching this video.